So the EVW model, we had started talking about this last time, and now in lab, I think we're a little ahead here. So you've seen this now through your labs, what we're talking about with this formulation of the logistic regression model. And at its heart, it's really just a reorientation of the variables, the x variable, what were formerly the x variables, the predictor variables, into a more epi-friendly format, which has niceties to it. And so we had talked about, there's kind of like 4 letters here of note, what happens to the x variables. We can label them as exposures or control variables, and these are the things we actually go out and measure in the world. And then we could reorient the control variables and specify whether they're starring in the model as confounders or effect modifiers or both. Something that is something we don't emphasize as much in the course, so I think I'm gonna maybe work it into a few lectures from now, is that we also can control for mediators as well, not just confounders. So mediators are things that are on the causal pathway rather than confounding the causal pathway. And so controlling for them also will change your measure of association, but for different reasons. And so we'll talk more about that. But the main emphasis for now is confounding control, the V variables. So we were kind of revisiting the earlier example of this MRSA example just to show what happens to those models with this notation. And so we had a simple model with just an intercept and the exposure. This is kind of like the unadjusted model. Nothing's going on here. We have just alpha plus beta 1 times exposure. Here we have the SAS output below. And so this is beta 1 here. This is the exposure variable is previous hospitalization. And so this model has no V's and no W's, is what you would say. And so going forward for a number of lectures, we're really going to write the models with just E and V and W. We're not even necessarily going to write the variable names here. And that will also make for like a cleaner look. Here was the model a model that controlled for age, sex, and previous antimicrobial use. And you can just look at this model and be like, yes, this model has an exposure and 3 confounders, because we have our 3 control variables, at least. We're not using V's yet, but I could be writing V's here as well. We're controlling for age, sex, and PMAMU. This should be a C. That's funny. What happened? I swear these got screwed up. This should be 1, 2, 3 rather than 2, 3, 4, and this should be. I'm sorry about that. That's frustrating. You can write this honestly whichever way you want. But we can do that. We can make that 2, 3 if we wanted. Or we could keep them consistent. It doesn't really matter because we're going to replace some of these in a moment. Whoops. Now it has frozen. So this is an EVW model with 3 control variables, and they're all starring in a confounding role. V1, V2, V3 is age, sex, and PMU. These C variables, these control variables, are all being controlled for as confounders. The reason that we're saying they're being controlled as confounders is because they're being controlled for and they don't involve the exposure. There's no product with the exposure. They're not interaction terms. And so we're saying we're controlling for them because we think they are playing a confounding role of the exposure-disease relationship. That's why they're in the model. But they're not W's. They're not W's because they're not involved in interaction terms with the exposure. So, so here is an example. This is another one of the models that we showed where, in the previous slide set, where we have age, sex, and PAMU here as all alone by themselves as confounding control variables, and then here they are again in product terms of the exposure. And in this situation, we're going to call them effect modifiers, right? And they're effect modifiers because, as we showed, let's say with the odds ratio for the exposure-disease relationship changed across values of these variables, right? You got a different odds ratio for the exposure when you were 35 versus when you were 60. And so anytime you have these other extraneous variables multiplying the exposure variables, they're going to kind of wind up acting in an effect modification role in the model. And so here we have the same three variables, C1, C2, C3, but they appear twice. Okay, they appear twice, one as confounding control and one as effect modifiers. And we're going to give them two different letters. Okay, and the reason we're going to give them two different letters now, instead of just calling them all the same thing, is because in our evaluation of the model, in our model selection strategy, and when we're like figuring out what to do with the model, is this the right model? What is the right model? How do we remove variables? We're going to address the W's in a different way than the V's. And so we're going to kind of label them separately, and we're going to say like, yes, it is true that W1 and V1 are both age, but we're going to use different notation to kind of remove those pieces. So that's why we're doing this. This is not just for fun. And so here's a crazier model. Okay, this is one we didn't show before, but here's a model that has a whole lot of stuff going on, and I'm going to just throw the bottom up here. Here we've got exposure, the C variables by themselves, C1 squared, C2 times C3, EC1, EC2, EC3, and then EC2, C3. Okay, so that looks kind of crazy, but why might we have these other variables? Well, first of all, what if the association between the log odds and age is not linear? So, okay, so here we have C1 in the model here, just by itself, this term. What does that mean to have a continuous age variable in your logistic regression model, just by itself? It means you have this very strong assumption that age moves linearly with the log odds, right? This is a linear relationship, right? And so that's a pretty strong assumption. Or you could say that the 1 over 1 plus e to the minus age relates to the probability in a linear fashion. So it's a little bit of an odd assumption, perhaps, and maybe you need to kind of allow for extra nuance to the relationship between age and the odds of disease, the log odds of disease. And so you might consider quadratic terms, cubic terms, or other things that kind of remove you from this linear assumption. And then you might test that. You might say, okay, maybe I'll allow for a quadratic term in the model. And so I'm sure you've seen these kind of terms in linear regression before. It's a little funky, perhaps, in logistic regression because it's like the log odds is now linearly related to these things, to these, or to continuous variables, or it's quadratically related to the log odds. But you may not know the shape of this relationship, but you may just put the terms in to see what happens. And then you say, okay, this cubic term was totally unnecessary, I'm going to drop that. And you might decide that later. That all being said, so you have the C1 squared term in the model. Well, it too is a confounder, right? It is being controlled for still in a quadratic kind of, this quadratic term is being controlled for in a confounding kind of way. Right, you are controlling for the age squared so that you might better understand the exposure-disease relationship. And therefore, I'm actually going to call age squared another V, V4. It, too, is another confounding term. Bless you. And here we have another thing, C2 times C3. This is allowing for interaction between sex and PAMU, both of which are control variables. So what that is allowing is, not just interactions with the exposure term, which is one type of interaction that you may have, but what if it is true that sex and PAMU have a statistical interaction with the log odds of disease, which is in this case is resistance to antibiotics. So if there's other interactions that don't involve the exposure, those might be important and real and true and all of that, but they're still actually technically confounding control variables in the sense that you are dealing with this phenomenon so that you can better understand the exposure-disease relationship. And so even though it's a product, it's an interaction term, it's still a V. And so we call that V5. Now, when you start to include them with statistical products, interaction terms with the exposure, then they're actually, again, effect modifiers. And so here we see that age, sex, and PEMU are all being multiplied in this beta 789. They're all being multiplied with the exposure. And then here we have a three-way interaction of exposure, C2, and C3. And that is itself a W. So you would say E times W4. But this represents the interaction of sex and PMU, and that's multiplying the exposure. Okay, so we're rewriting a three-way interaction term as just E times W4 is what we're going to do here, and it's going to simplify things a whole lot. This is ugly, right? We'd like to be able, even if this is the right model, what if this is exactly the truth? It's ugly and it's hard to deal with and it's unwieldy, and so we're going to use this notation to clean it up. And so here's how you might do that. So we're substituting here by color, and here we can rewrite this model as the thing on the bottom. And when we write it as the thing on the bottom, it becomes a whole lot easier to read. So we have alpha plus beta times exposure plus all these gamma terms times V variables, which are the confounding control variables. And then we have 4 delta terms, which are what we're going to call the betas for the effect modifiers, times E times W1, E times W2, 3, and 4. Okay, so a few things happened here. We got rid of the other betas and replaced them with other Greek letters. What that lets us do is we're only going to focus for most of our inference on the beta times exposure. This is the main thing of interest. This is why we did the study, and this is other stuff we're going to have to deal with. And so by not calling everything beta, that's going to be helpful in focusing on what we actually care about. These V variables are going to have gammas associated with them, and these are going to separately index our 5 confounders. So you can look at this model and be like, ah, yes, there are 5 confounders. Ah, yes, there are 4 effect modifiers. If it was beta 10, you'd have to actually pause and dissect what is going on here. And this is actually less approachable, and also this will distill into easier formulas to work with. So 1 beta, 5 gammas, 4 deltas, okay, and each representing a different kind of effect in the model. And then here we have a single W4 that actually, by the way, represented 2 other variables in there, C2 and C3, but now it's just a simple E times W4. Same model, same idea, but we've simplified the notation or streamlined the notation a bit. So formally, this is kind of what just happened here, right? We have D and E, just disease exposure. We have some C variables, the stuff to control for, and those are made into the V's and the W's. Okay, they're defined, and these might be the C's themselves or functions of C's, C squared, C1 times C2, whatever. Those are all things to control for as confounders, and they just become a V. And the effect modifiers are a similar idea, but they appear as product terms with E. So everything in our model can be distilled, everything on the right side of the equal sign can really be distilled as belonging to being either an E, a V, or a W. And that is really, really useful. Okay, so how would you, in this new formulation of the model, we can write the model a simpler way or a different way that kind of that really formalizes this classification into different units of things going on. And so here, you can write the logistic model as not just 1 over 1 plus e to the minus alpha plus beta 1, x1, x2, x3, and lots of betas and lots of x's. But we're just going to simply write it as alpha plus beta times exposure plus the sum of all the gammas times the v's plus the sum of all the deltas times the EW terms. Okay, this now says I got a model, it's got an intercept, an exposure, confounders, effect modifiers. And that is your epi universe all in one equation. You can write the logit form of that similarly like this, right? So when you logitify it with the logit function. You're doing the log odds of the probability, and then when you do that, it becomes a linear function that looks like this. And when you have the same exposure term here, this is E times W1, E times W2, and so forth. It's in this sum. This is a constant. You can factor out this constant and say E times the sum of the delta Wj's. And so this is the nice way to write the model, the EVW model. Right, we have alpha plus beta times exposure, sum of the gammas times V's plus exposure times the sum of all these pieces. For any given person, they're going to have the same value of the exposure. That's what lets us. That's why when I said E was a constant, why do we factor it? We can factor it out. It's because this is just the same constant term for within a given person, and it can be factored out of the summation. Okay, so this is our model rewritten to explicitly represent confounding and effect modification. Okay, so what happens to other things we've seen? So the odds ratio expression and I'm saying here parentheses one exposure. If you have multiple exposures, this is a little more complicated because you have several betas. But in the single exposure situation, what used to be maybe this formula, which I showed at the end of the last lecture, this was when we were just calling, I put a C in here, I could have put X in here to represent, and these were terms that were in interactions with exposure. And I said this was the odds ratio when there is interaction with exposure. To rewrite this using the EVW language would be E to the beta plus the sum of the deltas times the W's. And remember, this represents that, here we go, I'm just going to put this all up here. Do you remember this pattern that we saw before in the odds ratio expressions, that the confounder terms, these things that were just by themselves that had no exposure in them, they kind of all canceled out in the odds ratio expression. They all just go away. Well, that's again what this is saying here. There's no V's in this formula. It's just E to the beta plus the sum of the deltas times the W's. Okay, so this gives you, when you have effect modification at certain levels of those effect modifiers, age is this, sex is that, and so forth. You plug those values in here, you take the regression coefficients, and wow, you've got yourself an odds ratio for these levels of for these levels of W effect modifiers. So that's the idea. So what's really nice is you can just say, oh yeah, I've got V terms. I don't need these for the odds ratio. Oh, I've got three EW terms. I'm going to need these for the odds ratio. So you very quickly see what you need and what you don't. So the beauty here is the gamma terms are gone, and we just said all this. Now this model just separates things into distinct concepts. What I like about this is that you index each type of variable separately. So you don't just have 20 betas, you know exactly how many terms of each type that you're dealing with. That becomes very helpful. I have 4 EW terms, I've got 3 V terms and so forth. So what does this look like? So notice that I'm just kind of doing a parallel structure to the previous lecture. We kind of went through the model form, the odds ratio form, and then statistical inference with the model. In the EVW model, what does it look like to start doing hypothesis testing and confidence intervals? Obviously, it's the same machinery that we talked about earlier, but now we just represent it a little bit differently. So here's one model that we've shown already, the one that just controls for confounding on age, sex, and PAMU, has no effect modification in it. 3 V terms, one beta times exposure term. And so we said there's kind of 3 main things we care about generally with logistic regression. What is the odds ratio? What's the p-value associated with that odds ratio being, typically with is it a null result? Is the null hypothesis? Is it an odds ratio of 1? What's the significance of that test? And what's the confidence interval around the odds ratio? There's more things we care about. We care about the probability of disease itself, which we've talked about a little bit, and we may also be interested in the risk ratio. And so we're going to have a whole lecture just about risk and risk ratio. But more commonly found is odds ratios in the logistic literature, though I would say things are actually moving towards risk ratios. So this one we all know about already when we have this model. When we have a single exposure model, we know already that the odds ratio is not going to involve the V terms. So the odds ratio for exposure is just e to the beta. Right? We know this already. We're happy with this. There's no effect modification. To test the significance of this odds ratio being a null result or not, or a null value or not, we're talking about the hypothesis test of beta is 0, or alternatively, e to the beta equals 1, right? E to the 0 is 1, and this also would mean a null finding. And so we use the likelihood ratio or the Wald test for that. And then this is the formula that we saw earlier around the confidence interval for this odds ratio. So this is old news when you have a no W terms in your model. And we know how to do this. So let's say this was our output from earlier. E to the beta is e to the 1.4855, 4.417 was the estimated odds ratio. So note some stuff that SAS is giving you here. Sorry, so here is, we didn't actually show the output last time, but this is these are the three main tables that you might care about for this model. These are the three big pieces. This is where you get the -2 log likelihood for this model that you might use in the likelihood ratio test. It's this thing right here on the lower right. And it has to be intercept and covariates. This is the likelihood ratio of a model that has just the intercept in it, which is not really useful. Unless you were specifically testing a model that had exposure only. Let's say you had a model, logit P of X equals alpha plus beta times exposure, and you wanted to know, is the exposure significant in that model with nothing else in it? Then you might compare the model with intercept and covariates to intercept only because there's only one covariate, and then you'd be testing the beta times exposure. So that's a really specific situation. This is not very useful, but this is useful. Here in this table, analysis of maximum likelihood estimates. We've seen pieces of this table before. And here on the row that says previous hospitalization, that's the exposure term. Here's the beta term. Here's the beta hat estimate. Here's its standard error. And this is the Wald information. Wald chi-square statistic plus its p-value. This is exactly equal to, whoa. Was I wrong? I'm right. This is the Wald statistic, which is the estimate over the standard error squared, because this is the chi-square formulation. So remember, I said this could be either a z or a chi-square 1 degree of freedom. The chi-square version is the square of the z version of the statistic, and so this is the estimate over the standard error squared. That is exactly this, and this is the p-value on the chi-square 1 degree of freedom distribution. So SAS didn't have to do this. You could have done this is really just computing things on the two left columns. You could have done this in Excel for fun, but so it's convenient that it gives it to you here. This column contains nothing new over the two ones to the left, and here is the table of the e to the betas. And so here, 4.417 is the point estimate. And by the way, here's this is the Wald confidence interval, which you would get from this formula. So if you did e to the beta hat plus 1.96 times the standard error of beta hat, you would get exactly this. And by the way, you also could have gotten, you would use these two pieces to do that. So 0.4032 is the standard error of that estimate around previous hospitalization, right? So the standard error represents the uncertainty with which we are estimating this. And so you put those two pieces together and bam, you've got a confidence interval. Okay, so these are the three key pieces that you need to do your statistical inference. Specifically, what does the likelihood ratio test look like? So remember we said before the likelihood ratio test requires you to run two models. It's not as easy as the Wald statistic where you just look within your one model and there's the answer. you need to look at the -2 log likelihood statistic from 2 runs of the model. And so here's one run of the model. It's, I'm putting that table up here. This is that same table again. So here's the full model that you would look at. And the reduced model that's of interest for understanding the significance of the exposure, the odds ratio associated with exposure, beta. The reduced model looks like this. It's a model that has just the confounder terms and the intercept. Right? So we want to know, remember, the point of the likelihood ratio test is to say, does the likelihood meaningfully and significantly change when we drop the thing of interest, and so the thing of interest is beta, the exposure. And so we run that model. We get on the bottom here, we run the second run of the model, and then here is the new -2 log likelihood. It's this thing. And we use the formula presented earlier, which is the reduced models, -2 log likelihood minus the full ones. And we get a value of 16.1. That's really, really significant on the chi-square 1 distribution, which has a cutoff of 3.86 or so for 95%, or for p-value 0.05. And then, so this is way bigger than that. This is 16.1. Okay, so this involves 2 runs of the model. There's really, so it could be maybe kind of annoying. You can write a little macro, and we actually might still have it on Blackboard. I at one point just had a little macro that would run your model twice. You say, hey, run this model, drop this variable, and we just run it twice and give you the p-value. And actually, I'll put it up in a few weeks after or maybe I guess maybe one more week, after we do model selection strategies, which is going to be Dr. K jumping in. I actually have a macro that does everything. So it's going to do this, it's going to do all the model selection and work through some of the pieces that we're going to present around strategies for arriving at the best model. So it's called proc EVW, and it's going to kind of do all this. But in order for it to make total sense, we got to get through those other lectures where we talk about the specific selection strategies. And they're different ones than what was done in biostatistics. And so anyhow, for now, you can do this pretty manually by running it twice. It's not too bad. So Model 2 was a little more of a complicated model. Model 2 was the one that this is not the most complicated of the ones that we saw. This one has beta times exposure, and then the same 3 variables, age, sex, and PMU. They star in 2 roles. They're V's as confounding control, and they're also used to control for effect modification as W's 1, 2, 3. And so here they are over here. Here's one way to write the model: alpha plus beta times exposure. Gamma 1, V1, so forth, and then delta 1 times E times W1, and then up to delta 3, E times W3. Okay, we can simplify the way we write this, first of all. This is the simpler way to write the model. Right? We just use these summation signs and say, yeah, we've got 3 confounders and 3 effect modifiers. And so here's what the output for that would look like in SAS. It's going to be traditional stuff. So SAS doesn't know that these are E's and V's and W's. This is all just betas to SAS. But here's what those pieces look like. Well, what is the odds ratio expression for, what is the odds ratio expression given all of this? What's the odds ratio expression for the exposure? And so we can use our handy formula that says, okay, we'll grab the beta times exposure, and then look at the deltas. Right, that's all we need to do. We don't look at the V's. And this is our expression, which is that. And we take the estimated betas and deltas and plug them into this formula. And so here, 0.0559, what is that? Well, that's previous, whoops. That is this estimate here. That is the beta hat estimate from SAS. What is the delta 1 hat? Well, that's the coefficient for age times exposure. So that's this down here. Delta 2 hat is 0.4819, and then 1.1693. That's this last one on the bottom. So we need to grab these 4 things from our output. And now this is the magic formula to generate odds ratios for exposure from this model. So you got to be you got to know to do this. So once you start having interaction terms, you cannot rely on this table anymore. Okay, this table is not going to give you the odds ratio that you care about. It gives you something. These are interesting, but they don't really have validity once you have effect modification. You need to know, hey, I got to troll through the output and start collecting stuff. And it's going to be collecting this beta hat and then these 3 delta hat terms. Okay, and I'm going to even show you on a few more slides how we can even automate this slightly through the use of the contrast or estimate statements. In the absence of those, you got to just know what you're looking for here. So once you start having effect modification and your output becomes complicated, having this formulation of your model is helpful because you got to ignore some things and then pick out the other things. And so the statistical inference for this is complicated. I suggested this on the previous slide, on the previous lecture, which was that the confidence interval around this odds ratio is not straightforward. This whole expression has a standard error associated, in a sense, or you need to combine the standard errors for all of those pieces. There's 4 things that were estimated here: beta hat, and then 3 delta hats, 1, 2, 3. This whole thing has uncertainty around it. It's not just the uncertainty around a single estimate. You need the joint statistical uncertainty around the whole thing, and the whole expression. And that is not natively easy to find. It requires this formula, actually, down here on the bottom. Okay, so it involves taking the variance of each of those pieces, the sum of the variances, and the sum of all the pairwise covariances. And then you need something called the covariance matrix, or the variance covariance matrix, which will give you everything. So this is actually going to get really complicated the more complicated your odds ratio is. You're going to be doing this. I'm a little cute person that this may not feel so cute, but so this is complicated basically, and you need to ask SAS to give you this matrix of coefficients to plug into all of this. So once you start getting complicated odds ratio expressions that involve more than one variable, you really just want to use the contrast and estimate statements to get the confidence interval and to do a hypothesis test around one of these odds ratios. And so the hypothesis test really might be, you might test several different odds ratios to see whether any of them are equal to 1. And so you're going to use the contrast or estimate statements, and it will compute this for you. It is going to do this huge expression here, the sum of all the variances plus the pairwise covariances. It's going to do that for you. But what you got to do is tell it what the L looks like. So you have to, the trick becomes now not computing all this. It's actually just correctly instructing SAS what kind of odds ratio you want. Because it doesn't know that you want beta and then delta 1, delta 2, delta 3. So you got to say, these are the 4 things I'm interested in. Now give me the confidence interval around that. Okay, so what we're going to do, here, I'm just going to throw it all up here. Okay, so here was the odds ratio expression that we showed earlier. Okay, this was at 0.0559, 0.001 times age, and so forth. This is our generalized kind of expression for the odds ratio in this model. And now we want to actually estimate this thing and get its confidence interval and maybe do a statistical test for given values of those W variables, right? We want to say, like, I've got 3 values of age, sex, and PAMU, and I want to plug them in and start estimating what the effective exposure is. So here is how you do it. So let's say I have a 40-year-old male with previous exposure to antibiotics. What that means here is 40-year-old, okay, that's the value of age, male. That's the value, that was coded as 1 in the data. And then previous antimicrobials was also a 1. So what that actually means is I need to be plugging in this expression means I need to be plugging in 40, 1, and 1 in here to get what I want. So that's what you need to tell SAS to do. You need to tell SAS, I need 41 in 1. And the way we do that is by using the contrast or the estimate statements. And the syntax looks like this. You say contrast, and then you give it in quotes. You have to call it something, so it knows what to label the thing you're asking for in the output. So I would err on the side of descriptive, age 40, sex 1, PAMU. When you could like call this, ice cream, but like it's not going to be helpful. So do something helpful, and then after that starts the actual work. What you've got to do is tell SAS which variables which terms in the model you want to estimate in your L hat in your this it's called a linear contrast. This thing, what variables are in it, and what are the coefficients associated with them? And so you're going to say previous hospitalization 1. Well, what's that about? That was up here. This is saying beta time. This is saying the exposure is 1. They're right here. I didn't write parentheses 1, but this 0.0559 is the exposure, right? This was beta times exposure, and so beta. This is that beta, and then times exposure is 1. This person was exposed, and so it's an invisible 1 here, but you got to specify that there. This is because we're comparing exposed versus unexposed. So here's exposure 1, and then here are the 3 EW terms. Previous hospitalization times age, 40, that's this. Previous hospitalization times sex is 1, and then times PAMU is 1. Okay, so what terms are not in here? Age, sex, and PAMU on their own. Right? They're not here. We don't need them. Okay? So they are not in this expression. If you could put them in, if you really wanted to, and you'd have to type a 0 after. You'd say age 0, sex 0, PAMU 0, and that would make them go away again if you really wanted to see them in here. Or you just write the things of interest, right, which would be these 3 EW terms. Okay, so the name of the game is you got to know what terms you want, and then you got to correctly specify the coefficients. Okay, it's going to get a little more complicated when you use a class statement. So we can talk about that. This is good. This is easier when we have just kind of simple binary coefficients like sex 0, 1, PAMU 0, 1. Then you just write 1, 1, and it gets easier. If you have more complicated variables, these contrast and estimate statements will get a little more complicated, and we'll see that. So, but right now it's 41 in 1, and then here's the 3 terms, 41, 1. Then, if you're using the contrast statement, you have to do estimate equals exp for exponentiate this, please. And that's what this is down here. So if you don't specify this, it's going to be on the logit scale. The estimate's going to be the log of the actual thing you want, and you want to say, hey, SAS, please exponentiate that. And so that's the way you do it here, estimate equals exp. That's the contrast statement. There's this other thing called the estimate statement, which has almost the same syntax, and you have to write /exp instead of estimate equals exp, and then CL is I want confidence limits. It won't, by default, give you the confidence interval associated with this thing. So every SAS procedure is different, and not every SAS procedure necessarily has both contrast and estimates. Certain ones, actually I think in SAS 9.4, everyone has an estimate statement. The estimate statement kind of came around later. And so maybe in 9.4, I think everyone has this. The estimate statement in general is more designed for computing an estimate, like an odds ratio and its confidence interval, not necessarily for doing hypothesis testing. So not every estimate statement is set up for hypothesis testing in the way that the contrast statement is. It's still weird, it's annoying, it's duplicative, it's SAS. So SAS is, I'm sure as you're realizing, is kind of this thing that's been around for 35 years, and it's really a ball of Band-Aids in many ways, in that there's just fixes and patches, and certain procedures are not consistent, or just things are outmoded. So like proc reg, for example, which I'm sure you dealt with in 591P, it doesn't have a class statement. And every other SAS procedure does, and that's annoying. So this is just the way it is. Right now, proc logistic uses both. I kind of like estimate statements more. It's my thing. Does this seem reasonable? Make sense? Questions? Okay. Very well. So this is what happens. I'm going to put in, so what's cool about the estimate and contrast statements is you can put a lot of them below your model, right? This is just one specific kind of profile of person, a 40-year-old male with previous antimicrobial use, right? But there's really a lot of potential values here to the odds ratio depending on what level of the W terms you're at, right? If I'm different ages, different biological sexes or whatever. So here you can just literally put in SAS right below each other a whole bunch of contrast or estimate statements, and then you can just it will just kind of stack them into a nice table for you. And this gives you kind of the range. This gives you all of your odds ratios, right? And so here's a fancy way to do it. I'm arranging it into a more palatable table here. But here, if just looking at this, you can see there's this general pattern. I arrange them actually so that they kind of are in descending value here, which is so the highest odds ratio, the most at-risk person for resistance is the 35-year-old male with previous antimicrobial use. Oh, sorry, the 50-year-old. Sorry, the 50-year-old, then the 35-year-old, and then these are kind of lower risk kind of situations. The lowest risk being here we go, the 35-year-old female without exposure to antimicrobials has the smallest odds ratio. Here's all the confidence intervals associated with that. As you can see, some of these confidence intervals are not themselves statistically significant, right? So here these are wide intervals crossing 1, right? So we 0.2 to 11.8. So what's interesting is that when you start, even if you have some significant, let's say this was really the right model to use, and let's say you determined that everything was statistically significant and had to be in your model, and this is the best model, what you still sometimes find is that certain odds ratio expressions themselves will be statistically significant and certain ones won't. And there's going to be different levels of variability associated with them. For reasons that we can go into if you're interested. But basically, the results are not going to be like every confidence interval is significant, or the same level of precision. And so here we see that for just a few groups, do they have statistically significantly elevated risk, and the other groups, not so much in this model. So really, it's these highest risk groups that wind up being, we have enough precision to say that, yes, this is truly elevated risk for resistance. Everyone else, these point estimates are high, but not so much. We can't actually, we don't have enough faith in our data to actually conclude that. So despite these point estimates. So this is really ugly, right? And you might be saying, oh God, I don't ever want to report this model because my answer is not like the answer is 6. It's that I'm reporting 8 answers. And so here's maybe one nice way to present it, right? So there's ways to make your displays of information more digestible. Here, I'm using a table where the rows have one variable, here it's age, and then in columns, in kind of 2 nested column headers, we've got male, female, and then we have the exposed to antimicrobials on the left, and then on the right we have no. So these are the 3 W variables inside the table margins, and what we're showing in the cells is the odds ratio for the exposure. And this is maybe an easier way to show what's going on. And you'll see actually in the PROC EVW program that we'll talk about, it actually makes things kind of like this, and it also makes graphical plots of the odds ratios that kind of break them out in these ways and makes kind of graph, because you can almost imagine, what if I made a graph that showed all of these odds ratios and their confidence intervals, and there's ways to make graphs for that, and we'll go into that as well. So this is scary but manageable, is what I'm trying to say. Scary but manageable. So Okay, so we have, this is our model 2 still. We talked here about how to specify the odds ratios and the confidence intervals associated with them. But we may actually want to do actual hypothesis testing for the purpose of maybe dropping terms from the model rather than just reporting on the significance of these individual odds ratios. And so, what if we want to start evaluating, well, maybe this interaction term is not statistically significant, we don't need it. Right? And how do we go about doing that? And then if they're significant or not, what are we going to do to our model to reflect that information? And this is really what we're going to talk more about in the modeling strategy lectures. But what does this look like in SAS for this kind of model? Well, to test for any interaction, this is the chunk test kind of idea, where you say we're going to look at all of the interaction terms together and determine whether they're statistically significant. The easiest way to do that is with the likelihood ratio test that we talked about earlier. The wall tests are just testing single variables at a time. And so the likelihood ratio test looks at the likelihood ratio in this full and reduced model. The full model is this, and the reduced model considers dropping the interaction term, the effect modifier terms, more precisely. And so a likelihood ratio test testing delta 1, 2, and 3 equals 0 with chi-square with 3 degrees of freedom for chi-square distribution for that. Oh no, I lost my microphone. These don't last. The battery. This is so wasteful. The drawer is full of dead batteries. I mean, just anyway. Hello? Okay. So the likelihood ratio test. Okay, so if we want to test for effect modification, it's going to be a 3 degree of freedom test because we're thinking about dropping 3 terms. That's 3 degrees of freedom. And this is what that might look like. This is the model that we were just looking at that had all of our EW terms. This was its likelihood ratio, negative 2 log likelihood. It was 277.21. Should be up here somewhere. Okay, I don't want to go back too far. Believe me, this is it. And then if you drop the 3 W terms and you refit the model, which is model 1, we saw this earlier, it had just age, sex, and PMU and no EW terms. This was its negative 2 log likelihood here. And then you set up your likelihood ratio statistic as the difference between these two. And all right, it doesn't actually, there it is, I missed it, I thought it was on the bottom. Okay, so if you take the difference here, it's 2.096. That is remarkably not significant of a p-value. The cutoff value is going to be well above 4, I would say, at 0.05, alpha equals 0.05. The p-value for this is going to be like 0.6 or something. So you're going to say, I'm going to take the difference of this, and you're going to say, I have a chi-square degree of freedom value test statistic that's equal to 2.096. The probability of that is going to be not significant. So how do you find that p-value? Well, you might use a chi-square table. You can use the chi-square functions in SAS. Right? You can use the prob chi function in SAS to find that p-value, or any of the other ways that you might want to go find a p-value. Also, the macro that we'll post also will go over that. We'll actually automatically generate the p-value for you. But so anyway, this is not significant. Okay, so what you might say is, it looks like we would fail to reject the null hypothesis because we don't have. Yeah, we've failed to reject the null hypothesis. We don't have enough statistical certainty to do that. And so you have evidence to believe that there is no interaction at all. Okay, so what do you do next? Okay, so you actually have 2 pathways here, even though I kind of make it look like you have 1. This is still maybe our recommended thing. You could just drop the EW terms because collectively they are not statistically significant, or you can still actually consider backward elimination of the E times W terms. What I mean by that is you can now still do individual statistical testing on them. This is kind of I believe the one that's more endorsed in our text, and the one that the author of the text, Dr. K, would endorse. I still actually think that if this is remarkably not significant, you may actually consider dropping the effect modification terms. The reason why you might still look and test these individually is that what if one of them is highly significant and the other two are remarkably not significant? The combination, the union of that information may still be a statistical test that's not, a hypothesis test that's not statistically significant. This showed up in linear regression when do you remember the ANOVA table? That thing, that mean squared error, and the sums of squares, mean squares, F statistic as you go to the right. That test, that F statistic, you probably learned it was a not very powerful test. You weren't supposed to really use it. Does people remember that? People say it's not a powerful test, and the reason it's this global F test. It's the, hey, is anything in the model significant test? And it's a very not powerful test because you're lumping together maybe some things that are significant, maybe some things that aren't, and maybe it just kind of washes out and you can't actually detect anything in your model. This is a global test across a whole lot of things, and maybe you missed something. And so if you think maybe you missed something, you might still look at the interaction terms individually. So what does that look like? What do I mean by backward elimination of the EW terms? You might do something that looks like this. You might say, okay, I'm going to go down, I'm going to look at the output from my model, and I'm going to say, I see my three EW terms here. These are the deltas. And then look at these are the walled p-values, let's say. I'm going to now, so none of them look very statistically significant, but I'm going to drop the term that is the least significant. Okay, so that's this 0.601 here associated with previous hospitalization times age. Then I rerun the model and reevaluate, and now you can say, looks like previous hospitalization times sex is 0.6735. That's a higher p-value than PAMU. Let's drop it and rerun the model, and then the remaining EW term is still 0.212, and then you would say drop that too, because it doesn't meet some threshold. You might say maybe it has to be 0.05 or 0.1 or whatever it's going to be to keep it in the model. So this showed up in biostatistics as the backwards elimination method. In this course, we're only going to apply it to effect modifier terms, and this is really what the model selection strategy stuff is going to be about. We're going to only do this for effect modifiers and not confounders. So the V variables get treated differently. We're not going to do that. Why, does anyone know why we might not do that? Why are we only statistically testing these terms to stay in the model? Are you supposed to statistically test for confounding terms? No, we do other things. Right? We more qualitatively assess the bias, the confounding bias, because you can't actually statistically test for a conceptual thing like confounding. And so this statistical algorithm of backwards elimination might be valid in this case when we're looking at EW terms, interaction terms. Interaction is an actual statistical process, and so we do apply statistical inference to it. We're going to do something else for the effect for the V variables, but for these W's, we're going to keep them or not keep them potentially through these kind of approaches. So this is backwards elimination with the walled test. You could have also done it with the likelihood ratio test. You could have you could have run this model, the top model, and then the middle one that drops, each of the, let's say that drops previous hospitalization times age and done that likelihood ratio test. And then you actually could have dropped each one of these one at a time and done all the likelihood ratio tests and done a likelihood ratio based backwards elimination rather than the walled version. That would take a lot longer, and that's not going to be so fun. But luckily, the proc EVW macro actually will do this for you as well. So it's going to do all of the backwards elimination for EW terms and all of that. And so you could do this, you can do it kind of through serial commands in SAS, or you can use this macro that we'll put online. So this is the idea, what you're going to do in this model. So that is going to basically be the kind of where we're going to stop on the EVW stuff before we switch to other topics. But we're going to come back to all of this in modeling in the model selection strategies in about 2 lectures. We're going to come back to kind of thinking more deeply around how do you deal with a more nuanced EVW model? What is the right model? There's like 20 competing versions of the right model, and how do I get there to the right answer? Or at least a credible answer, or several credible answers. The last thing here, these last few slides are an interesting, it's interesting. It used to be a more necessary thing maybe to teach around here, and not as much so anymore. And what I mean by that is SPSS used to be more commonly used at Rollins than I think it is now. And SPSS is a package that does not have the contrast or estimate statement type equivalence. It doesn't have a custom way for coming up with those odds ratio expressions. Most of the other packages, Stata and R, all have it, but SPSS specifically didn't, which has really been a long-time favorite of like of the social sciences for statistics. And so there's a way to actually trick the computer into giving you the equivalent of a complicated odds ratio expression inside of just that basic odds ratios table, the ones that's just the e to the betas table. And the way to trick it is this really ugly slide. And I want to just, I'm not going to, I don't think this is as essential, so this is just FYI in case you need to know this for SPSS, or you just want to appreciate what it's doing. You make new X variables in your model, in a data set actually, or in your data that are different versions of your X variable, of your variables. And what you're going to do is they're going to be minus a constant, okay? So what I mean by this is, let's say I remember we did the first contrast statement, we wanted to know the odds ratio when somebody was 40, okay? Someone's 40. Well, the constant, if I wanted to know that odds ratio without having to use a contrast statement, I would subtract make a new variable called age 40 or whatever you want to call it, and it's going to be age minus 40, the whole column in your data set. Okay, what happens is now when you define such a variable, when you do this delta expression, this is the odds ratio expression, what's going to happen is delta is going to cancel out because everything is minus 40, and you wanted to know the odds ratio when age was 40. It's going to cancel out, and you're going to be left with a special e to the beta in this weird model where age is now defined as age minus 40. It's going to magically cancel out, and if you do this for everything in your contrast statement, you will have an e to the beta, this weird beta, but in this model, with your reformulated data, the e to the beta estimates the contrast that you care about. So you have to subtract all these constants. It's interesting, but really only if you have to use a pack. If you're like on a desert island and you don't have SAS and you only have SPSS or whatever it is, and you need a contrast statement in order to signal the helicopter or whatever it's going to be, this is how you do it, okay? So and it's worth appreciating that it's a cool trick and everything will cancel out. So you can go follow this through at home. Oh, here it is. Look at that. I just said it. So you're defining an alternative model that subtracts all these constants that you care about, and they're going to actually all go away because when I plug in, hey, 40 sex and equals 1 and PMU equals 1, these all become zeros and it all goes away. Is the idea. Okay, so here's the SAS code for how to do that, which is of course silly because SAS already does it, right? So, but here this formalizes what I just said. This is the original way to do it, in using actually a contrast statement. Here is the alternative coding here. I forgot, you only need to do this to the W variables. You don't actually need to do it. You don't need to store age minus 40 on its own. You just make these funny interaction terms here that subtract the things of interest. And now, oops, sorry. Here, this is the standard method. This is the alternative. Here, this is the odds ratio for that contrast statement, 8.56. The regular e to the betas table correctly has 8.564 as the odds ratio for previous hospitalization. So this, in the alternative weird model, is this. Okay. So, again, desert island. Or if you have to use SPSS because you're being told to in some way. So the next topic, which kind of is, in a sense, in the sequence of what we're doing in the course, is the last kind of binary logistic regression general model thing to think about before we move into model selection strategy, which is, okay, now that you know all the fun of logistic regression, how do you arrive at a good model? Then we're going to talk about diagnostic issues, and then we're going to talk about other versions of logistic regression. So where this fits in, we're going to talk about matching, which is really this alternative form. It's going to involve an alternative form of the logistic model called conditional logistic regression. And that will conclude all you need to know in general about the binary logistic model before we move into these other things to do with it. Model selection, diagnostic issues. And then we'll talk about prediction and risk ratios as well. So that's where we're going here. So, and some of this stuff with matched analysis is going to be very similar to what we started with in 534. You'll see it's the same, very similar graphics and similar slides. But we're going to move into, previously I ended in just talking about how to do this with stratified table-based methods. We're going to move it into the logistic regression framework and talk about, okay, how do you accomplish the matched analysis inside of logistic regression? What we'll see is that it's a much more powerful technique to do this inside of logistic regression because many variables that you want to control for, you actually could not do previously when we did like the matched McNamara table stuff. And so the logistic model is going to be way, way favored for matched data, which, as you all know, is very commonly found in the case control design, but not exclusively. We use it for other things. We use it in other study designs as well. So we're going to talk about kind of three pieces: the kind of what is matching, how do we analyze matched data, and then some other issues that come up with matched data around its analysis. And so within the analysis of matched data, there's the old way and the new way, or less old way, the stratified analysis, and then the logistic regression analysis and matched data. So, this is a slide that we've seen, that I think we've had before, that kind of talks about all of these are six major methods for statistical control or control inside of studies and analyses. And then this was matching. This was the idea that you intentionally construct your exposed or your unexposed or your diseased and not diseased if it's a case control study. You intentionally construct these match samples that are balanced on the covariates. Okay, so you are playing God, and what you're doing is you're recruiting your people to exactly have the same covariate distributions so that you won't have confounding. Okay, that's the idea. You're not just going to go out and sample the world in some haphazard way. You're going to very intentionally do this. And it comes at a cost, but it also comes with a benefit, which is a very good confounding control on the things that you've intentionally made your matched sets upon. And so, again, this comes up in every, matching can be used in any situation, and it's called different things. In experimental designs, it's called blocking, and this was the original use of matching. Way back when, in the early 20th century, when a lot of modern statistical inference was being developed. So this is all of this is so new. None of this existed more than a century ago. Statistical inference in the regression mindset came up in agriculture, agricultural studies, and we would divide fields into blocks, which would be these grids, and they would say like, okay, we're going to put fertilizer X here and fertilizer Y, and which plants grow taller, and all of that. So that was, they would use blocks, and they would divide them up, and it was basically a form of matching. It was called blocking. Okay, it's a very big overview of that. Okay, so and those were agricultural field experiments, and so we now think of matching in terms of typically in the case control study, but sometimes in cohort studies, particularly the retrospective design, where you might have a bunch of people in, let's say, a hospital. Let's try to think of hospital X, and you have all these people that were exposed to something, and you have data on their outcomes, but you may not have a control group. You may have a retrospective list of people at that hospital, however, who did not get the exposure, and you might match them to a historical registry of other people at the hospital. So that is it's a cohort in some sense, because it's longitudinal data, it's not prospective, but it's over time. But you had to match to find your controls in some way, or you made a comparison group out of a matched thing. So that's a retrospective matched case cohort design. So when dealing with certain types of situations and data, and really with registries, is where you will often see this kind of situation, matched cohorts. You can also have prospective matched cohort, and you can do whatever you want. Someone gives you the money for it. But the case control study is really where we see matching come up a lot. So more formally, what does this mean? It means when we select a comparison group that looks like an index group. That's maybe the most general way to think about it. We go and we very purposively select control people that don't have the thing of interest. If it's exposure, we look for unexposed that look like the exposed. If it's a case control, we're looking for controls that are different than the cases. And so why do we do this? The major reason is confounding control. Okay, we're not just going to go get anybody from the community and just hope that the comparison is valid to our cases. We have 10 people show up and they're got some very strange thing, and we want to make a case control study, we want to figure out what's going on. We're not just going to go find any 10 people that live nearby. We only have a few cases, and we're not going to let statistical variation or bias or whatever get in the way. We want to make the best study we can, and we're going to use matching. So it's very, very good for confounding control, and particularly when you have very complex confounding. Okay, so and when you could say, well, I don't need a control for, let's say you wanted to you were considering matching on age and let's say you want to match on age and race, and you could say, well, I could just do a study and collect data on age and race, and then control for it on the back end later. I'll just put those in my model, I'll stratify them or whatever, and I'll deal with them analytically. And that might be possible, but when you have really complex confounders, like so let's say twins or geography, or household, there's certain constructs that are really difficult, that are potentially very strong confounders, and you may want to deal with them very efficiently, and you might match based on those. So I can't, if I right, let's say family or household, right? That's a very complicated set of exposures. To measure all of the things that go into to deconstruct what it means to live in your house, or to have grown up in your house, or whatever it is, that might be like a complicated set of 1,000 variables that I don't really feel like measuring, and many of them might be confounders of interest. So one way to just, in a kitchen sink way, deal with the complex exposure environment of your household is to actually recruit a control from your household, and then match based on that, and now I've balanced, I have one exposed and one unexposed from your household. And that's it. And now I've dealt with confounding on all of the weird stuff that went on in your house growing up, or maybe not. I don't know. Maybe I was weird. But right. So, but that is how you. I'm sorry, but I just insulted everyone in the room. But I mean, but the idea is that household, neighborhood, there's, are very complicated, and so to explicitly measure that isn't fun, and that's why we might do matching. The other piece is precision, and so again, by controlling for all this extraneous stuff through matching, I might actually get a very precise answer, a much more precise answer than if I, put the 1,000 terms that represent your household in the model. That might actually result in a big inflation of my confidence interval for the thing I care about. And that really suggests this other piece, which is variable reduction. So again, I could explicitly measure a whole bunch of confounders and put them in the model, but that means I have to go and measure 50 things, 100 things. And I might just say, no, I'm going to match based on neighborhood. And that's going to control for all that's going on in that neighborhood. It's a single entity. It's just neighborhood. And I don't have to explicitly measure a whole lot of stuff. And so these are all intertwined reasons why you might want to match. It's a complicated call that's specific to a given study situation. And so here in the case control study, we're going to call them cases and controls. And then here in a cohort or a trial, you might call them matching on the exposed and the unexposed in some way. Remember, the case control design is a backwards design. We start with diseased and undiseased cases and controls, and we look backwards in some. We reverse what we're doing, and we're going to start measuring exposures, right? And then it's this kind of study design on its head, and we use those associations to talk about the risk of being a case. And so it's a little crazy, but the cohort in RCT is more on the surface understandable because you start with exposed and unexposed. So here, these are the people that we introduced last spring, where they were. This little graphic represents like race and male, female, and then old, young, or skateboarder, worker, briefcase person, traveler, air traveler, whatever it is, we have skateboard traveler and air traveler. So, or I use them to represent like young and old, or something. I use them for age before. This is not, excluding older skateboarders or younger workers, but that was the idea. So these little graphics will represent kind of how we construct match sets. And so matching kind of can happen in two general flavors. That, again, is a continuum of how you really do this. But the idea of individual matching is what you're most familiar with, which is I've got a case, whose cases are usually rare entities in your study. You may only have 15 cases showing up with something unusual, or you may have they have this outbreak and there's 15 cases. And so you have these individual cases, and you very specifically find a control that matches that case. Right? That's individual matching. And for every case, you're going to go do this. And you might do it in an exact way or in a category way, which means like I might say I need to have exactly an 18-year-old versus I'll take anyone between 15 and 20. But the idea here is that you're very specifically doing matching to the individual. And the other style is called frequency matching, where you just have the distribution of the factors and the controls match the cases, that of the cases. And I graphically show this here. So here's individual matching. I got a case who's female, 14-year-old, green. I'm going to go find a control that looks exactly the same. And you do this on all of the factors that you're matching on. Purple, 33-year-old case, old, and then you go find the same control. So the problem here is that this is not always feasible, right? So the more things you want to control on, the more difficulty you're going to have finding controls. If I want to simultaneously, match for 6 factors, that's going to be interesting, right? Because I want to look for neighborhood and age and race and this and that, and it turns out you find no one that actually, can serve as or is willing to serve as a control. Or you run into this issue you can't even identify who these people are. Becomes problematic. So here's maybe a slightly easier way, which is you can do, this is perhaps called caliper matching, some people might call it that, where basically you look at ranges, and you say, well, I'll take any 10 to 15-year-old to serve as a control for a 14-year-old. This is probably what's more commonly done is you kind of loosen up on some of your criteria. But what also occurs, particularly in the retrospective cohort design, that example where I talked about registries and matching using historical data to controls, you see something more like this, which is the frequency matching, where you're not really, you're not doing you're not finding a specific control to a specific case per se. You're saying that the distribution in the control group overall matches of these factors that are confounding factors, sex, age, and race. It overall will match the distribution in the cases, right? So you're not saying like I need to go recruit a specific person. You're gonna construct a data set of controls that is more or less comprised of the same mix of people as the cases. Okay, so this is what you see most often in the historical case control or historical cohort designs. This is easier. And you may even do something even looser, which is what I said here, which is you independently match the distribution. So what I mean by that is you say, okay, this sample was 50%, let's say 60% female. I want my group to be 60% female. They're this percent old, and then the next percent's going to be old. They're independently considered rather than jointly considering the distribution of sex, age, and race. You can do this whichever way you want. Okay, there's a lot of ways to do it, and they're all getting at the same idea, and some may be more or less feasible than others. Obviously, this is perhaps a little bit of a looser idea than individual matching, and maybe will get you something a little bit less, perhaps. Okay, so again, there's lots of. I'm just going to end here with what do you do? Which do you choose? And again, it's about convenience and feasibility, and particularly when you think about matching, it's how. Not only is like what makes the most statistical sense, but what's feasible in terms of what can I identify in people in the population. Not every factor I want to control for is going to be like people aren't going to wear it on their heads. Like I have this blood type, and so there's a lot of operational challenges to this, and so whether the availability of people and the types of data you have are going to determine all this. Okay, we'll pick this up on Tuesday. Have fun this Labor Day weekend.